Picture this, a massive rock hurtling through space, not just any rock, but one that holds secrets older than our planet. Asteroids, those ancient remnants of our solar system, are more than just floating debris. They are cosmic time capsules, preserving clues about the universe's earliest days. But here's the twist: scientists have found things on these asteroids that defy logic, challenge our understanding, and sometimes leave us scratching our heads in wonder. From metallic spheres that shouldn't exist to organic molecules that hint at the origins of life, these discoveries are rewriting the story of our solar system. In this video, we're diving into 30 of the most bizarre and mind-blowing findings scientists have uncovered on asteroids. You'll hear about water ice hiding in the most unexpected places, strange magnetic fields that shouldn't be possible, and even asteroids that are more like rubble piles than solid rocks. Each discovery is a piece of a puzzle, revealing just how little we truly know about these mysterious space travelers. So, buckle up and get ready to explore the weird, the wild, and the utterly unexpected. By the end of this journey, you'll see asteroids in a whole new light, and you might just question everything you thought you knew about the cosmos. Let's dive in. Now, turning to the first of these bizarre discoveries, let's talk about metallic spheres found on asteroids. Imagine stumbling upon perfectly round, metallic objects floating in space. Sounds like something out of science fiction, right? But these spheres are very real. Scientists have discovered them on several asteroids, and their composition is just as fascinating as their existence. These spheres are primarily made of iron and nickel, metals that are typically found deep within planetary cores. So how did they end up on the surface of asteroids? The leading theory suggests that these metallic spheres are remnants of ancient collisions. Billions of years ago, when the solar system was still young, massive impacts between asteroids or even protoplanets could have exposed their metallic cores. Over time, these fragments were ejected into space, eventually cooling and solidifying into the spherical shapes we see today. Another intriguing possibility is that volcanic activity on some asteroids could have played a role. If an asteroid had enough internal heat, molten metal could have erupted to the surface, forming droplets that later hardened into spheres. These metallic spheres aren't just curiosities, they're windows into the violent and chaotic early days of our solar system. By studying them, scientists can piece together the history of asteroid collisions and the processes that shaped these ancient bodies. It's a reminder that even the smallest objects in space can hold some of the biggest secrets. And this is just the beginning. Next, we'll explore how organic molecules on asteroids might hold the key to understanding the origins of life itself. Now, turning to the next fascinating discovery, let's dive into the detection of organic molecules on asteroids. These molecules are not just random compounds, they are the building blocks of life as we know it. Imagine tiny, carbon-based structures floating through space, carrying the potential to spark life itself. Scientists have found these organic molecules on several asteroids, and their presence is a game-changer in our understanding of how life might have begun on Earth. Organic molecules include things like amino acids, which are essential for creating proteins, and nucleobases, which form the backbone of DNA and RNA. The fact that these molecules exist on asteroids suggests that they could have been delivered to Earth billions of years ago through asteroid impacts. This idea, known as panspermia, proposes that life's ingredients might have hitched a ride on space rocks, seeding our planet with the necessary components for life to emerge. But how did these molecules form in the first place? The early solar system was a chaotic place, filled with swirling clouds of gas and dust. Within these clouds, chemical reactions could have occurred, creating complex organic compounds. Over time, these compounds became embedded in asteroids, preserving them like cosmic time capsules. By studying these molecules, scientists can learn about the chemistry of the early solar system and how it set the stage for life to develop. The discovery of organic molecules on asteroids also raises intriguing questions about the possibility of life elsewhere in the universe. If these molecules can form and survive in the harsh environment of space, could they have done the same on other planets or moons? It's a tantalizing thought that keeps researchers searching for answers. As we continue to explore these ancient space rocks, we're not just uncovering the secrets of our own origins, we're also gaining insights into the potential for life beyond Earth. And with that, we move forward to another astonishing find: the presence of water ice on asteroids and what it means for the future of space exploration. Now turning to another groundbreaking discovery, let's explore the surprising presence of water ice on certain asteroids. For years, asteroids were thought to be dry, barren rocks, but recent findings have completely overturned that assumption. Scientists have detected water ice on several asteroids, and this discovery has profound implications for our understanding of these celestial bodies and the future of space exploration. Water ice on asteroids is a game-changer for several reasons. First, it challenges the long-held belief that asteroids are devoid of water. This ice likely formed billions of years ago, preserved in the cold, shadowed regions of these space rocks. Its presence suggests that water, a key ingredient for life, is more widespread in the solar system than we once thought, but the implications go even further. Water ice on asteroids could be a vital resource for future space missions. Imagine a future where astronauts extract water from asteroids to drink, grow food, or even produce oxygen and rocket fuel. This concept, known as in situ resource utilization, could revolutionize space travel by reducing the need to carry heavy supplies from Earth. Instead, missions could refuel by tapping into the water reserves of nearby asteroids, making long-term exploration and even colonization of space more feasible. The discovery of water ice also raises questions about how it got there in the first place. Some scientists believe that comets, which are rich in ice, may have collided with asteroids, depositing water in the process. Others suggest that water could have formed directly on asteroids through chemical reactions involving hydrogen and oxygen. Whatever the origin, this ice provides a fascinating glimpse into the history of our solar system and the processes that shaped it. As we continue to study these icy asteroids, we're not just uncovering clues about the past, we're also paving the way for humanity's future in space. And with that, we move forward to another intriguing find: the strange magnetic fields detected on some asteroids and what they reveal about these mysterious objects. Now turning to another fascinating discovery, let's delve into the strange magnetic fields detected on some asteroids. Unlike the magnetic fields we're familiar with on planets like Earth, these asteroid magnetic fields are far more unusual and mysterious. Scientists have found that certain asteroids possess magnetic fields that are not only weaker but also irregular in shape and strength, raising questions about how they formed and what they reveal about these space rocks. One of the most intriguing aspects of these magnetic fields is their origin. On Earth, our magnetic field is generated by the movement of molten iron in the planet's core. But asteroids, being much smaller and lacking the same internal dynamics, shouldn't logically have magnetic fields at all. So, how do they? One theory suggests that these magnetic fields are remnants from the early solar system, preserved in the asteroid's metallic core. Another possibility is that they were created by intense heat and pressure during ancient collisions, which temporarily magnetized the asteroid's materials. These magnetic fields also provide clues about the asteroid's internal structure. For example, the presence of a magnetic field could indicate that the asteroid has a metallic core, which would make it a potential target for future mining missions. On the other hand, the irregularity of these fields might suggest that the asteroid's interior is fragmented or uneven, possibly due to past impacts or internal stresses. What's even more fascinating is how these magnetic fields interact with their surroundings. Some asteroids with magnetic fields have been observed to influence nearby dust and smaller particles, creating unique patterns or trails. This interaction could help scientists better understand the asteroid's surface composition and how it has evolved over time. As we continue to study these magnetic anomalies, we're not just uncovering the secrets of individual asteroids, we're also gaining insights into the broader processes that shaped our solar system. And with that, we move forward to another remarkable find, the discovery of rubble pile structures, which reveal a surprising truth about how some asteroids are held together. Now turning to another astonishing discovery, let's explore the concept of rubble pile structures found on some asteroids. Unlike the solid, monolithic rocks we often imagine, these asteroids are essentially loose collections of smaller rocks, dust, and debris, all held together by gravity. This revelation has completely transformed our understanding of how asteroids form and maintain their structure in the harsh environment of space. The idea of rubble pile asteroids challenges the traditional view that these celestial bodies are solid and unyielding. Instead, they are more like cosmic jigsaw puzzles with pieces that can shift and move over time. Scientists believe that these rubble piles are the result of countless collisions over billions of years. When asteroids collide, they don't always shatter into nothingness. Sometimes, the fragments are pulled back together by gravity, creating a loosely bound aggregate. One of the most fascinating aspects of rubble pile asteroids is their surprising stability. Despite being made up of loosely connected materials, they can maintain their shape and structure for millions of years. This stability is largely due to the weak gravitational forces that hold the pieces together, combined with the lack of external forces strong enough to pull them apart. However, this delicate balance also means that these asteroids are more susceptible to disruption from future impacts or even the gravitational pull of nearby objects. The discovery of rubble pile structures has significant implications for our understanding of asteroid formation and evolution. It suggests that many asteroids may have undergone multiple collisions and reconfigurations throughout their history, rather than forming as solid bodies and remaining unchanged. This insight has also influenced how scientists approach asteroid missions. For example, landing on a rubble pile asteroid would require careful planning, as the surface could be unstable and prone to shifting. Moreover, the study of rubble pile asteroids provides clues about the early solar system. By analyzing their composition and structure, scientists can piece together the history of collisions and interactions that shaped the asteroid belt. These findings not only deepen our knowledge of asteroids, but also shed light on the processes that influenced the formation of planets and other celestial bodies. As we continue to unravel the mysteries of these cosmic rubble piles, we gain a clearer picture of the dynamic and ever-changing nature of our solar system. And with that, we move forward to another intriguing discovery, the existence of binary asteroid systems where two asteroids orbit each other in a delicate cosmic dance. Now turning to another fascinating discovery, let's delve into the world of binary asteroid systems. These systems consist of two asteroids orbiting each other, locked in a gravitational dance that offers unique insights into the dynamics of space. Unlike solitary asteroids, binary systems provide a rare glimpse into how celestial bodies interact and influence one another in the vast expanse of the cosmos. The formation of binary asteroid systems is a complex process, often triggered by collisions or gravitational interactions. When two asteroids come close enough, their mutual gravitational pull can cause them to orbit one another, creating a stable pair. In some cases, a larger asteroid may capture a smaller one, while in others, a single asteroid might split into two due to rapid rotation or a collision, forming a binary system. These systems are not just random pairings, they are the result of precise conditions and forces at play in the asteroid belt. One of the most intriguing aspects of binary asteroid systems is what they reveal about the history of our solar system. By studying their orbits and compositions, scientists can piece together the events that led to their formation. For example, the distance between the two asteroids and the shape of their orbits can indicate whether they were formed through a collision or a capture event. This information helps researchers understand the frequency and nature of asteroid interactions over billions of years. Binary systems also challenge our understanding of asteroid stability. While they may appear fragile, these pairs can remain bound together for millions of years, their orbits finely tuned by the delicate balance of gravitational forces. However, external influences such as the gravitational pull of nearby planets or other asteroids can disrupt this balance, potentially causing the pair to separate or collide. This dynamic nature makes binary systems a key area of study for understanding the long-term evolution of asteroids. The study of binary asteroid systems has practical implications as well. For instance, missions to these systems could provide valuable data for planetary defense strategies. By understanding how binary asteroids behave, scientists can better predict the trajectories of potentially hazardous asteroids and develop methods to deflect them if necessary. Additionally, binary systems offer unique opportunities for scientific exploration, as they allow researchers to study two distinct bodies in close proximity, providing a wealth of data about their composition, structure, and history. As we continue to explore these cosmic duos, we uncover more about the intricate relationships that shape our solar system. Binary asteroid systems remind us that even in the vastness of space, connections and interactions are at the heart of celestial evolution. And with that, we move forward to another remarkable discovery: the existence of moons orbiting asteroids, a phenomenon that further blurs the line between asteroids and planets. Now turning to another astonishing discovery, let's explore the phenomenon of asteroid moons. Yes, you heard that right, asteroids can have moons of their own. These tiny celestial companions orbit their parent asteroids, creating miniature systems within the asteroid belt. The discovery of asteroid moons has not only expanded our understanding of these space rocks, but also challenged our assumptions about their complexity and behavior. So, how do these moons form? One of the most common theories is that they are the result of collisions. When two asteroids collide, debris can be ejected into space. If the conditions are just right, some of this debris may be captured by the gravitational pull of the larger asteroid, forming a moon. Another possibility is that a passing asteroid or gravitational interaction with a planet could strip material from an asteroid, which then coalesces into a moon. These processes highlight the dynamic and often chaotic nature of the asteroid belt. The presence of moons around asteroids also provides valuable insights into gravitational interactions in space. For instance, the size and distance of a moon from its parent asteroid can reveal information about the asteroid's mass and density. By studying these relationships, scientists can better understand how gravity shapes the structure and evolution of asteroids. Additionally, the existence of moons suggests that even small bodies in space can have complex gravitational systems, much like planets. One of the most famous examples of an asteroid with a moon is Ida, a large asteroid in the main belt. In 1993, the Galileo spacecraft captured images of Ida and its tiny moon, Dactyl. This discovery was groundbreaking as it provided the first clear evidence that asteroids could have moons. Since then, dozens of other asteroid-moon systems have been identified, each offering new clues about the formation and history of these celestial bodies. Asteroid moons also play a role in our understanding of planetary formation. Some scientists believe that these systems could be remnants of the early solar system, offering a glimpse into the processes that led to the formation of planets and their moons. By studying asteroid moons, researchers can piece together the puzzle of how small bodies in space evolve over time and how they contribute to the larger structure of the solar system. As we continue to explore these fascinating systems, we uncover more about the intricate relationships that govern the cosmos. asteroid moons remind us that even the smallest objects in space can hold profound secrets waiting to be discovered. And with that, we move forward to another intriguing topic: asteroids with unusually high metal content, a discovery that could have significant implications for both science and industry. Now turning to another fascinating discovery, let's delve into asteroids with unusually high metal content. These space rocks, rich in elements like nickel and iron, are not just scientific curiosities. They could hold the key to future space exploration and even industry. Imagine an asteroid made almost entirely of metal, glinting in the sunlight as it drifts through the void. These metallic asteroids are thought to be the remnants of ancient planetary cores, shattered by collisions billions of years ago. Their composition makes them incredibly dense and durable, standing out from the more common rocky or icy asteroids. The potential economic value of these metal-rich asteroids is staggering. For instance, a single asteroid could contain trillions of dollars worth of precious metals like platinum, gold, and rare earth elements. These materials are essential for modern technology, from smartphones to renewable energy systems. Mining these asteroids could revolutionize industries on Earth and provide the raw materials needed for building infrastructure in space, such as space stations or even colonies on other planets. However, the challenges of asteroid mining are immense. Extracting metals from an asteroid in the harsh environment of space requires advanced technology, precise planning, and significant investment. One of the biggest hurdles is the sheer distance and difficulty of reaching these asteroids. Unlike mining on Earth, where resources are relatively accessible, asteroid mining would involve navigating the complexities of space travel, including long distances, microgravity, and the need for autonomous or remotely operated equipment. Additionally, the process of extracting and refining metals in space is still in its infancy, requiring innovative solutions to overcome the lack of atmosphere and extreme temperatures. Despite these challenges, the potential rewards are too great to ignore. Companies and space agencies around the world are already exploring the feasibility of asteroid mining, with some even planning missions to test the technology needed to extract resources from these celestial bodies. If successful, asteroid mining could not only provide a new source of valuable materials, but also reduce the environmental impact of mining on Earth by shifting some of the demand to space. As we continue to study these metal-rich asteroids, we uncover more about their origins and potential. They remind us that the resources of our solar system are vast and largely untapped, offering opportunities for both scientific discovery and economic growth. And with that, we move forward to another intriguing topic: the evidence of ancient volcanic activity on some asteroids, a discovery that sheds light on the early thermal history of the solar system. Now turning to another remarkable discovery, let's explore the evidence of ancient volcanic activity on some asteroids. These findings are not just fascinating, they offer a glimpse into the fiery past of our solar system. Imagine an asteroid not as a cold, lifeless rock, but as a once active volcanic body, spewing molten material into the void of space. Scientists have identified features on certain asteroids that suggest they were once home to volcanic eruptions, similar to those seen on planets like Earth or Mars. These volcanic features, such as solidified lava flows and volcanic domes, indicate that some asteroids were once hot enough to melt their interiors. This molten material would have risen to the surface, creating the volcanic landscapes we now observe. The presence of these features challenges the traditional view of asteroids as inert, unchanging objects. Instead, it suggests that they were dynamic worlds, shaped by intense heat and geological activity billions of years ago. The discovery of volcanic activity on asteroids provides crucial clues about the early thermal history of the solar system. During its formation, the solar system was a chaotic and energetic place, with countless collisions and the decay of radioactive elements generating immense heat. This heat could have melted the interiors of some asteroids, leading to volcanic activity. By studying these ancient volcanic features, scientists can piece together the conditions that existed in the early solar system and better understand how planets and other celestial bodies formed. One of the most intriguing aspects of these volcanic asteroids is what they reveal about the diversity of objects in our solar system. Not all asteroids are the same. Some are rocky, some are metallic, and some, as we now know, were once volcanic. This diversity highlights the complex processes that shape the solar system and underscores the importance of studying asteroids to uncover its history. As we continue to explore these volcanic asteroids, we gain new insights into the forces that shaped our cosmic neighborhood. They remind us that even the smallest objects in space can hold the key to understanding the grand story of the solar system. And with that, we move forward to another fascinating topic, the discovery of carbon-rich asteroids, which contain complex organic compounds and offer tantalizing clues about the building blocks of life. Now turning to another extraordinary discovery, let's delve into the world of carbon-rich asteroids. These celestial bodies are not just rocks floating in space, they are treasure troves of complex organic compounds, offering tantalizing clues about the origins of life itself. Imagine an asteroid packed with carbon-based molecules, the very building blocks that make up all living things on Earth. These asteroids are like time capsules, preserving the chemistry of the early solar system and providing scientists with a unique window into how life might have begun. Carbon-rich asteroids, often referred to as C-type asteroids, are among the most primitive objects in our solar system. They contain a variety of organic molecules, including amino acids, which are the fundamental components of protein. These molecules are essential for life as we know it, and their presence on asteroids suggests that the ingredients for life may have been widespread in the early solar system. Some scientists even speculate that these asteroids could have delivered these crucial compounds to Earth billions of years ago, seeding our planet with the raw materials needed for life to emerge. The discovery of carbon-rich asteroids has profound implications for our understanding of the universe. By studying these asteroids, researchers can gain insights into the chemical processes that occurred in the early solar system, long before planets like Earth formed. These findings help us piece together the puzzle of how simple molecules evolved into the complex structures that make up living organisms. Moreover, carbon-rich asteroids could hold clues about whether life exists or could exist elsewhere in the universe. Beyond their scientific significance, carbon-rich asteroids also hold practical value for future space exploration. The organic compounds found on these asteroids could potentially be used as resources for future missions, providing materials for fuel, construction, or even life support systems. Some scientists envision a future where we mine these asteroids for their valuable carbon-based materials, turning them into stepping stones for deeper space exploration. As we continue to study these fascinating objects, we uncover more about their role in the story of life and the solar system. They remind us that even the most unassuming rocks in space can hold the keys to some of the universe's greatest mysteries. And with that, we move forward to another intriguing topic, the observation of dust trails following certain asteroids, which reveal even more about their composition and history. Now turning to another fascinating discovery, let's explore the mysterious dust trails that follow certain asteroids through space. These trails, often faint and difficult to detect, are more than just cosmic debris. They are windows into the asteroid's past, revealing clues about its composition and the violent collisions it has endured over billions of years. Asteroid dust trails are formed when an asteroid is struck by another object, causing fragments of rock and dust to be ejected into space. Over time, these particles spread out, creating a trail that can stretch for thousands of miles. The size and shape of the trail depend on the force of the collision, the asteroid's composition, and the gravitational forces acting on the particles. Some trails are short and dense, while others are long and diffuse, painting a vivid picture of the asteroid's history. Scientists study these dust trails to learn more about the asteroid's surface and interior. The particles in the trail can provide valuable information about the asteroid's mineral composition, revealing whether it is made of rock, metal, or a mix of both. By analyzing the trail, researchers can also estimate the age of the asteroid and determine how often it has been hit by other objects. This information helps us understand the chaotic environment of the asteroid belt and the forces that have shaped these celestial bodies over time. One of the most intriguing aspects of asteroid dust trails is what they tell us about the asteroid's stability. Trails that are long and well-defined suggest that the asteroid has experienced significant collisions, which may have altered its shape or even broken it into smaller pieces. On the other hand, faint or irregular trails might indicate that the asteroid is relatively stable with fewer recent impacts. This knowledge is crucial for understanding the evolution of asteroids and predicting their future behavior. The study of asteroid dust trails also has practical implications for space exploration. These trails can pose a hazard to spacecraft, as the tiny particles can damage sensitive instruments or even puncture a spacecraft's hull. By mapping the trails, scientists can identify safe paths for future missions and reduce the risk of collisions. Additionally, the dust itself could be a valuable resource containing minerals or other materials that could be harvested for use in space. As we continue to observe and analyze these enigmatic trails, we gain a deeper appreciation for the dynamic nature of asteroids and the role they play in the solar system. They remind us that even the smallest particles in space can tell a story, one that helps us piece together the history of our cosmic neighborhood. And with that, we move forward to another intriguing topic, the bizarre shapes of some asteroids, which range from elongated to nearly spherical, and what these forms reveal about their origins and evolution. Now turning to another fascinating aspect of asteroids, let's delve into the bizarre and varied shapes these celestial bodies can take. Unlike the smooth, spherical forms we often associate with planets, asteroids come in a wide range of shapes. Some are elongated like cosmic potatoes, while others are nearly spherical, and some even resemble irregular lumps of rock. These unusual shapes are not random. They are the result of the asteroid's unique history, shaped by forces like rotation, collisions, and even gravity. One of the key factors influencing an asteroid's shape is its rotation. As an asteroid spins, the centrifugal force acting on it can cause it to stretch or flatten, leading to elongated or flattened forms. For example, some fast-rotating asteroids take on a shape similar to a spinning top, with bulging middles and tapered ends. This happens because the material on the asteroid's surface is pulled outward by the rotation, creating a distinctive profile. On the other hand, slower rotating asteroids may retain more irregular shapes, as the forces acting on them are not strong enough to reshape them significantly. Collisions also play a major role in determining an asteroid's shape. Over billions of years, asteroids in the crowded asteroid belt have been bombarded by other objects, leaving behind craters, fractures, and even reshaping entire bodies. Some asteroids are so heavily impacted that they resemble rubble piles, held together loosely by gravity. These collisions can break off large chunks of the asteroid, creating jagged edges or asymmetrical forms. In extreme cases, a collision can split an asteroid into multiple pieces, each taking on its own unique shape as it continues to drift through space. Gravity, or the lack of it, is another factor that contributes to the bizarre shapes of asteroids. Unlike planets, which have enough gravity to pull themselves into a spherical shape, most asteroids are too small to exert such a strong gravitational force. As a result, they retain their irregular forms, shaped more by external forces than by their own gravity. However, some larger asteroids, like Ceres, have enough mass to become nearly spherical, blurring the line between asteroids and dwarf planets. The study of asteroid shapes provides valuable insights into their formation and evolution. By analyzing the shape of an asteroid, scientists can infer its history of collisions, its rotation rate, and even its internal structure. For example, an asteroid with a smooth, spherical shape might have experienced fewer collisions or have a more rigid internal structure, while an irregular, lumpy asteroid could indicate a history of frequent impacts or a loose rubble pile composition. These unusual shapes also have practical implications for space exploration. Landing on an irregularly shaped asteroid, for instance, poses unique challenges for spacecraft, as the uneven surface and varying gravity can make navigation difficult. Understanding the shape of an asteroid is crucial for planning missions, whether the goal is to land on its surface, collect samples, or even deflect it from a potential collision course with Earth. As we continue to explore these oddly shaped celestial bodies, we gain a deeper understanding of the forces that shape our solar system. Each asteroid, with its unique form, tells a story of its journey through space, a story of collisions, rotations, and the relentless pull of gravity. And with that, we move forward to another intriguing discovery: the large cracks found on the surfaces of some asteroids and what they reveal about the internal stresses these bodies endure. Now turning to another intriguing discovery, let's explore the large cracks found on the surfaces of some asteroids. These cracks, sometimes stretching for miles across the asteroid's surface, are more than just superficial features. They provide a window into the internal stresses and history of these celestial bodies. Scientists believe these cracks form due to a combination of factors, including thermal stress, impacts, and even the asteroid's rotation. One of the leading theories suggests that thermal stress plays a significant role in creating these cracks. As asteroids orbit the Sun, they experience extreme temperature fluctuations. During the day, the side facing the Sun can heat up dramatically, while the side in shadow plunges into freezing cold. Over time, this constant cycle of heating and cooling causes the asteroid's surface to expand and contract, leading to the formation of cracks. This process, known as thermal fracturing, is similar to how repeated freezing and thawing can cause cracks in rocks on Earth. Impacts from other space objects also contribute to the formation of these cracks. When an asteroid is struck by another body, the force of the collision can send shock waves through the asteroid, creating fractures on its surface. In some cases, these cracks can extend deep into the asteroid's interior, revealing layers of material that have been hidden beneath the surface. These fractures can also weaken the asteroid's structure, making it more susceptible to further cracking or even breaking apart entirely. The rotation of an asteroid can also play a role in the formation of cracks. As an asteroid spins, the centrifugal force acting on it can create tension in its surface, especially if the rotation is fast or irregular. This tension can cause the surface to crack, particularly in areas where the asteroid's structure is already weakened by impacts or thermal stress. In some cases, these cracks can grow over time, eventually leading to significant changes in the asteroid's shape or even causing it to split into smaller pieces. These cracks are not just surface-level features, they provide valuable clues about the asteroid's internal structure and history. By studying the size, depth, and pattern of these cracks, scientists can infer the forces that have acted on the asteroid over time. For example, a network of deep, intersecting cracks might indicate a history of frequent impacts, while long, parallel cracks could suggest that thermal stress has played a major role in shaping the asteroid's surface. Understanding these cracks is also important for future space exploration. If a mission aims to land on or collect samples from an asteroid, the presence of large cracks could pose challenges. These cracks could make the surface unstable, increasing the risk of landslides or collapses. On the other hand, they could also provide access to deeper layers of the asteroid, offering a glimpse into its composition and history that would otherwise be inaccessible. As we continue to study these fascinating features, we gain a deeper understanding of the dynamic processes that shape asteroids. Each crack tells a story of the forces that have acted on the asteroid, from the relentless heat of the sun to the violent impacts of collisions. And with that, we move forward to another remarkable discovery, the rare phenomenon of asteroids with thin atmospheres and what they reveal about the surface processes of these enigmatic bodies. Now turning to another fascinating discovery, let's delve into the rare phenomenon of asteroids with thin atmospheres. While most asteroids are airless, barren rocks, a small number of them have been found to possess faint, temporary atmospheres. These atmospheres, though incredibly thin compared to those of planets, offer intriguing insights into the surface processes and composition of these celestial bodies. The formation of these atmospheres is often linked to a process called outgassing. Outgassing occurs when volatile substances, such as water, ice, or frozen gases trapped beneath the asteroid's surface, are heated by the sun. As the asteroid's surface warms, these materials sublimate, turning directly from a solid into a gas, and escape into space, creating a thin, temporary atmosphere. This process is most common in asteroids that contain significant amounts of ice or other volatile compounds, which are often found in the outer regions of the asteroid belt. Another factor contributing to the formation of these atmospheres is the asteroid's rotation. Fast-rotating asteroids can experience centrifugal forces that help release gases from their surfaces. Additionally, impacts from smaller space rocks can expose buried volatile materials, triggering outgassing and the creation of a temporary atmosphere. However, these atmospheres are often short-lived, as the low gravity of asteroids makes it difficult for them to retain gases. Over time, the gases escape into space and the atmosphere dissipates. The presence of these atmospheres provides valuable clues about the asteroid's surface composition and history. For example, the detection of water vapor in an asteroid's atmosphere suggests the presence of subsurface ice, which could be a potential resource for future space missions. Similarly, the identification of other gases, such as carbon dioxide or methane, can reveal information about the asteroid's chemical makeup and the processes that have shaped it over time. Studying these atmospheres also helps scientists understand the dynamic nature of asteroids. The formation and dissipation of these thin atmospheres are influenced by factors such as the asteroid's distance from the Sun, its rotation rate, and its surface composition. By observing these changes, researchers can gain insights into how asteroids evolve over time and how they interact with their environment. The discovery of asteroids with atmospheres challenges our traditional view of these objects as lifeless, unchanging rocks. Instead, it reveals them to be dynamic bodies with complex surface processes and hidden reservoirs of volatile materials. As we continue to explore these enigmatic objects, we uncover new layers of complexity that deepen our understanding of the solar system's history and the potential resources it holds. With this in mind, we now turn our attention to another remarkable feature of asteroids, the unusual impact craters that dot their surfaces, and what these craters reveal about the violent history of these celestial wanderers. Now turning to another intriguing aspect of asteroids, let's explore the impact craters that adorn their surfaces, particularly those with unusual features. While craters are common on asteroids, some stand out due to their unique characteristics, such as central peaks, multiple rings, or asymmetrical shapes. These features are not just random quirks, they hold valuable clues about the asteroid's composition, history, and the nature of the impacts that created them. Central peaks, for example, are often found in larger craters and are thought to form when the force of an impact compresses the asteroid's surface, causing material to rebound upward. These peaks can reveal information about the asteroid's internal structure, as the material that forms them often comes from deeper layers. By studying these peaks, scientists can infer the strength and density of the asteroid's subsurface, providing insights into its overall composition. Multiple ring craters, on the other hand, are even more complex. These craters feature concentric rings of raised material surrounding a central depression, resembling ripples on water. They are typically formed by extremely powerful impacts, which send shock waves through the asteroid, causing the surface to fracture and collapse in a series of rings. The presence of multiple rings suggests that the asteroid experienced a high-energy collision, and the size and spacing of the rings can help scientists estimate the energy of the impact and the properties of the asteroid's surface. Another unusual feature found in some asteroid craters is asymmetry. Unlike the neat, circular craters we often imagine, some craters are elongated or irregularly shaped. This can occur when an asteroid is struck at an oblique angle, causing the impact to spread unevenly across the surface. These asymmetrical craters can provide clues about the direction and angle of the impact, as well as the asteroid's rotation at the time of the collision. The study of these unusual craters is not just about understanding the past, it also has implications for the future. By analyzing the size, shape, and distribution of craters, scientists can assess the frequency and intensity of impacts in the asteroid belt. This information is crucial for planning future missions to asteroids, as it helps identify potential hazards and safe landing sites. Additionally, the material exposed by these impacts can reveal valuable resources such as metals or water ice that could be utilized in future space exploration. In essence, the craters on asteroids are more than just scars from ancient collisions. They are windows into the asteroid's history and composition. Each unusual feature tells a story, shedding light on the forces that have shaped these celestial bodies over billions of years. As we continue to study these enigmatic craters, we uncover new layers of understanding about the dynamic and ever-changing nature of our solar system. With this in mind, we now shift our focus to another fascinating discovery: the concept of asteroid families, groups of asteroids that share similar orbits and are thought to have originated from a single parent body. Now turning to the concept of asteroid families, we uncover another layer of intrigue in the asteroid belt. These families are groups of asteroids that share strikingly similar orbits, leading scientists to believe they originated from a single parent body, likely shattered by a massive collision in the distant past. Imagine a cosmic family reunion where each member carries a piece of the same ancestral story. These families are not just random clusters, they are fragments of a shared history, offering a unique window into the violent and chaotic events that have shaped the asteroid belt over billions of years. The formation of an asteroid family begins with a catastrophic collision. When a large asteroid is struck by another object, the impact can break it apart into countless smaller pieces. These fragments, now sharing similar orbital paths, drift through space as a cohesive group. Over time, gravitational interactions and other forces may slightly alter their orbits, but the family resemblance remains clear. By studying the orbits and compositions of these asteroids, scientists can trace them back to their common origin, piecing together the story of the collision that created them. One of the most well-known asteroid families is the Flora family, located in the inner region of the asteroid belt. This family is thought to have formed from a collision involving a parent body roughly 100 kilometers in diameter. The remnants of this ancient impact now number in the thousands, each carrying clues about the parent asteroid's composition and the nature of the collision. By analyzing these fragments, researchers have gained insights into the types of materials present in the early solar system and the processes that shaped it. Asteroid families also play a crucial role in understanding the history of collisions in the asteroid belt. The frequency and size of these families provide evidence of the intensity of past impacts, helping scientists estimate how often such events occur. This information is vital for assessing the risk of future collisions, not just among asteroids but also with Earth. By mapping these families, researchers can better predict the behavior of asteroids and identify potential threats to our planet. Moreover, asteroid families offer a unique opportunity to study the internal structure of their parent bodies. When an asteroid is shattered, the fragments that are ejected often come from different layers of the original object. By examining the composition of these fragments, scientists can infer what the interior of the parent asteroid looked like, much like piecing together a shattered puzzle. This has led to surprising discoveries, such as the presence of unexpected minerals or evidence of ancient volcanic activity. In essence, asteroid families are more than just remnants of past collisions. They are time capsules that preserve the history of the solar system. Each family tells a story of destruction and rebirth, offering clues about the forces that have shaped the asteroid belt and the broader cosmos. As we continue to study these families, we gain a deeper understanding of the dynamic and ever-evolving nature of our celestial neighborhood. With this in mind, we now shift our focus to another fascinating discovery: fast-rotating asteroids which spin so quickly that they challenge our understanding of their structure and stability. Now turning to the phenomenon of fast-rotating asteroids, we encounter a cosmic mystery that defies our expectations. These asteroids spin at astonishing speeds, some completing a full rotation in just a few hours. To put this into perspective, imagine a massive rock hurtling through space, spinning so fast that its surface could fling loose material into the void. This rapid rotation poses significant challenges for scientists trying to understand the structure and stability of these celestial bodies. One of the most intriguing aspects of fast-rotating asteroids is how they manage to hold themselves together. Typically, gravity is the force that keeps an asteroid intact, but when an object spins too quickly, centrifugal forces can overpower gravity, potentially causing the asteroid to break apart. This raises the question: how do these fast-spinning asteroids remain whole? Scientists believe that some of these asteroids may be held together by internal strength, such as the cohesion of their materials, or they might be loosely bound rubble piles that somehow resist disintegration despite their rapid spins. The study of these fast-rotating asteroids has led to surprising discoveries about their shapes. Many of them are not spherical but instead have elongated or irregular forms. This is because the intense centrifugal forces at their equators push material outward, creating a bulging effect. Over time, this can lead to the formation of bizarre shapes, such as elongated flying saucers or even dumbbell-like structures. These unusual shapes provide clues about the asteroid's internal composition and the forces acting upon it. Another challenge posed by fast-rotating asteroids is understanding their origins. Some scientists speculate that these asteroids may have been spun up by collisions or the gravitational influence of nearby objects. Others suggest that the Yorp effect, a phenomenon where sunlight exerts a tiny but continuous torque on an asteroid, could gradually increase its rotation over millions of years. Whatever the cause, the result is a celestial object that spins at a pace that seems almost impossible for something of its size. The implications of these fast rotations extend beyond just the asteroids themselves. They also affect how we approach space exploration and potential asteroid mining. For example, landing a spacecraft on a fast-rotating asteroid would be incredibly difficult due to the rapid movement and uneven surface. Additionally, the structural integrity of these asteroids could make them less viable targets for mining operations, as their loose or unstable nature might pose risks. In essence, fast-rotating asteroids are a testament to the dynamic and unpredictable nature of our solar system. They challenge our understanding of celestial mechanics and push the boundaries of what we thought was possible. As we continue to study these enigmatic objects, we gain not only a deeper appreciation for the complexity of asteroids, but also valuable insights into the forces that shape our cosmic neighborhood. With this in mind, we now shift our focus to another fascinating discovery: asteroid outgassing, a phenomenon where these rocky bodies release gases into space, revealing even more about their hidden secrets. Now turning to the phenomenon of asteroid outgassing, we uncover yet another layer of mystery surrounding these enigmatic space rocks. Outgassing occurs when asteroids release gases into the void of space, a process that might seem surprising given their rocky, seemingly inert nature. But as scientists have discovered, these gases can reveal a wealth of information about an asteroid's composition, history, and even its potential role in the early solar system. The gases released during outgassing typically include water vapor, carbon dioxide, and other volatile compounds. But where do these gases come from? One possible source is the sublimation of ice hidden beneath the asteroid's surface. When sunlight heats the asteroid, any subsurface ice can turn directly into gas, escaping through cracks or pores in the rock. This suggests that some asteroids, despite their dry and barren appearance, may harbor significant amounts of water ice, a discovery that has profound implications for our understanding of the solar system's water distribution. Another source of outgassing could be the breakdown of minerals within the asteroid itself. Certain minerals, when exposed to heat or radiation, can release gases as they decompose. This process not only provides clues about the asteroid's internal composition, but also hints at the conditions it has endured over billions of years. For example, the presence of specific gases might indicate that the asteroid formed in a region of the solar system rich in volatile materials, or that it has undergone significant heating events in its past. Outgassing also plays a role in shaping the asteroid's surface and behavior. As gases escape, they can carry dust and small particles with them, creating a faint atmosphere or even a temporary tail similar to that of a comet. This activity can alter the asteroid's appearance and even its trajectory over time. In some cases, the force of escaping gases can act like a tiny thruster, subtly nudging the asteroid into a new orbit. This phenomenon, known as the Yarkovsky effect, has important implications for predicting the long-term movements of asteroids, especially those that could pose a threat to Earth. Perhaps one of the most intriguing aspects of asteroid outgassing is what it tells us about the building blocks of life. The detection of organic molecules in the gases released by some asteroids suggests that these celestial bodies may have played a role in delivering the ingredients for life to Earth. This idea, known as panspermia, proposes that asteroids and comets could have transported water and organic compounds to our planet during its early history, setting the stage for the emergence of life. As we continue to study asteroid outgassing, we gain not only a deeper understanding of these fascinating objects, but also new insights into the history and evolution of our solar system. Each puff of gas released into space is like a whisper from the past, offering clues about the asteroid's origins, its journey through the cosmos, and its potential connections to life on Earth. With this in mind, we now shift our focus to another captivating discovery: the wide range of colors observed on asteroids, which provide further insights into their surface composition and history. Now turning to the vibrant world of asteroid colors, we uncover yet another fascinating layer of these celestial bodies. Asteroids, often imagined as dull, gray rocks, actually display a stunning array of colors ranging from deep reds to icy blues. These colors are not just for show, they provide critical clues about the asteroid's surface composition, history, and even its origins. The color of an asteroid is determined by the materials that make up its surface. For example, reddish hues often indicate the presence of iron-rich minerals or organic compounds, which have been altered by exposure to solar radiation over billions of years. These asteroids, known as S-type asteroids, are typically found in the inner regions of the asteroid belt and are thought to be remnants of the early solar system's building blocks. On the other hand, bluish or grayish asteroids, often classified as C-type asteroids, are rich in carbon and other primitive materials. These darker asteroids are more common in the outer regions of the asteroid belt and are believed to be some of the most ancient objects in the solar system. Their muted colors suggest they have undergone less alteration from solar radiation, preserving a snapshot of the conditions present during the solar system's formation. In addition to red and blue, some asteroids exhibit a mix of colors or even unusual spectral features. For instance, V-type asteroids associated with the asteroid Vesta have a distinctive greenish tint due to the presence of pyrozene, a mineral formed in volcanic processes. These colorful variations help scientists classify asteroids into different groups, each with its own unique characteristics and history. But how do scientists determine an asteroid's color? By analyzing the light reflected off its surface, researchers can identify specific wavelengths that correspond to different minerals and compounds. This technique, known as spectroscopy, allows them to create a color fingerprint for each asteroid, revealing its composition without ever touching it. These fingerprints not only help classify asteroids but also provide insights into their formation and evolution. The colors of asteroids also play a role in understanding their potential resources. For example, the reddish hue of an S-type asteroid might indicate a high concentration of metals like nickel and iron, making it a potential target for future mining missions. Meanwhile, the darker tones of C-type asteroids suggest they could contain water ice and organic materials, valuable resources for sustaining life on long-term space missions. As we explore the colorful diversity of asteroids, we gain a deeper appreciation for the complexity of these ancient objects. Each hue tells a story, from the fiery volcanic processes that shaped some asteroids to the icy, carbon-rich environments that preserved others. These colors are not just a visual spectacle, they are a window into the history of our solar system and the processes that have shaped it over billions of years. With this vivid exploration of asteroid colors, we now turn our attention to another intriguing discovery: the fragments of asteroids that have made their way to Earth, providing direct evidence of these distant objects' composition and history. Now turning to the fascinating topic of asteroid fragments on Earth, we uncover a direct connection between these distant space rocks and our own planet. Meteorites, which are fragments of asteroids that have survived the journey through Earth's atmosphere, provide scientists with invaluable clues about the composition and history of these celestial bodies. Unlike remote observations, meteorites offer tangible evidence that can be studied in laboratories, revealing secrets that would otherwise remain hidden in the depths of space. When an asteroid collides with another object or undergoes a catastrophic event, fragments can break off and drift through space. Some of these fragments eventually cross paths with Earth, entering the atmosphere as meteors. While most burn up due to the intense heat, a few survive the fiery descent and land on the surface as meteorites. These space rocks are like time capsules, preserving the materials and conditions of the early solar system. One of the most significant discoveries from meteorites is their composition. By analyzing their chemical makeup, scientists can determine whether they originated from S-type, C-type, or other classes of asteroids. For example, meteorites rich in iron and nickel are often linked to S-type asteroids, while those containing carbonaceous materials are associated with C-type asteroids. This direct evidence helps confirm the classifications made through remote observations and provides deeper insights into the diversity of asteroids. Meteorites also reveal the history of their parent asteroids. Some contain tiny grains of minerals that formed in the earliest stages of the solar system, offering a glimpse into the processes that shaped planets and asteroids billions of years ago. Others show signs of being altered by water or heat, indicating that their parent bodies experienced significant geological activity. These findings challenge the traditional view of asteroids as inert, unchanging rocks and highlight their dynamic nature. Perhaps one of the most exciting aspects of meteorites is their potential to carry organic molecules. Some carbonaceous meteorites have been found to contain amino acids, the building blocks of proteins, and other complex organic compounds. This discovery supports the idea that asteroids may have played a crucial role in delivering the ingredients for life to Earth, sparking the origins of life as we know it. The study of meteorites not only enhances our understanding of asteroids, but also provides a tangible link between these distant objects and our own planet. By examining these fragments, scientists can piece together the story of the solar system's formation and evolution, uncovering the processes that shaped both asteroids and planets. As we continue to explore these ancient relics, we gain a deeper appreciation for the interconnectedness of our cosmic neighborhood. With this exploration of asteroid fragments on Earth, we now turn our attention to another remarkable discovery: the surprising existence of rings around some asteroids similar to those found around planets. Now turning to the surprising discovery of asteroid rings, we find yet another example of how these celestial bodies continue to defy expectations. While rings are typically associated with planets like Saturn, scientists have discovered that some asteroids also possess these stunning features. This revelation has opened up new avenues for understanding the complex environments surrounding these small but fascinating objects. The first asteroid found to have rings was Chariklo, a relatively small body located in the outer solar system. When astronomers observed Chariklo passing in front of a distant star, they noticed something unexpected. The star's light dimmed not just once but multiple times. This pattern revealed the presence of two thin rings encircling the asteroid, much like the rings of Saturn. This discovery was groundbreaking as it challenged the assumption that only large planets could sustain such structures. So, how do these rings form around asteroids? One leading theory suggests that they are the result of collisions. When a smaller object collides with an asteroid, the impact can eject debris into space. If the debris remains within the asteroid's gravitational influence, it can settle into a stable orbit, forming a ring. Another possibility is that the rings are created by the asteroid's own rotation. If an asteroid spins fast enough, material on its surface could be flung outward, eventually forming a ring system. These rings provide valuable insights into the asteroid's environment and history. For example, the presence of rings suggests that the asteroid has experienced significant collisions or other disruptive events. The composition of the rings can also reveal details about the asteroid's surface and interior. By studying the way light interacts with the rings, scientists can determine the size and density of the particles, offering clues about the processes that shape them. One of the most intriguing aspects of asteroid rings is their potential to evolve over time. Unlike the rings of Saturn, which are relatively stable, asteroid rings may be more dynamic. They could dissipate over time as particles collide and drift away, or they might be replenished by new collisions. This dynamic nature makes asteroid rings a fascinating subject for ongoing research, as they provide a window into the ever-changing conditions of the solar system. The discovery of rings around asteroids has expanded our understanding of these small but complex bodies. It reminds us that even the smallest objects in space can hold surprises, challenging our assumptions and deepening our appreciation for the diversity of the cosmos. As we continue to explore these ringed asteroids, we uncover new layers of complexity in the solar system's history and evolution. With this exploration of asteroid rings, we now turn our attention to another intriguing phenomenon: the observation of changes on the surfaces of asteroids over time. Now turning to the fascinating phenomenon of asteroid surface changes, we uncover yet another layer of complexity in these enigmatic space rocks. Unlike the static, unchanging images we might imagine, asteroids are far from inert. Over time, their surfaces can undergo significant transformations, revealing a dynamic and ever-evolving nature. One of the most striking examples of these changes comes from observations of the asteroid Bennu, visited by the OSIRIS-REx mission. Scientists were surprised to find that Bennu's surface was not only covered in boulders but also showed signs of recent activity. rocks appeared to have shifted and small particles were seen being ejected into space. These observations suggest that asteroids are not just passive remnants of the early solar system, but active bodies with ongoing processes. So, what causes these surface changes? One major factor is impacts. Even small collisions with other space debris can dislodge material, creating new craters or altering the asteroid's surface texture. Over millions of years, these impacts can completely reshape an asteroid, erasing old features and creating new ones. Another cause is outgassing, where volatile substances like water ice trapped beneath the surface turn to gas and escape, sometimes carrying dust and small rocks with them. This process can leave behind pits or even cause the asteroid to change shape slightly. Thermal effects also play a significant role. As asteroids rotate, their surfaces are exposed to the intense heat of the sun and the cold of space. This constant heating and cooling can cause the surface material to expand and contract, leading to cracking and fracturing. Over time, these thermal stresses can break down rocks into smaller particles, altering the asteroid's appearance and structure. These surface changes are not just cosmetic, they provide valuable insights into the asteroid's history and composition. For example, the presence of fresh craters can indicate recent collisions, while the distribution of ejected material can reveal the asteroid's internal structure. By studying these changes, scientists can piece together the asteroid's past and predict how it might evolve in the future. The dynamic nature of asteroid surfaces also has implications for space exploration. For missions aiming to land on or collect samples from asteroids, understanding these changes is crucial. A surface that appears stable one day might shift the next, posing challenges for spacecraft operations. This unpredictability adds another layer of complexity to the already daunting task of exploring these distant objects. As we continue to observe and study asteroids, the discovery of surface changes reminds us that these small bodies are far more active and complex than we once thought. They are not just relics of the past, but dynamic worlds that continue to evolve, offering new insights into the processes that shape our solar system. With this understanding, we now turn to another intriguing aspect of asteroids, the evidence of past collisions between these celestial bodies. Now turning to the evidence of past collisions between asteroids, we uncover a dramatic chapter in the history of these celestial bodies. Asteroids, often thought of as solitary wanderers, have a long history of violent encounters that have left lasting marks on their surfaces and structures. These collisions are not just random events, they are key to understanding how the asteroid belt formed and how individual asteroids have evolved over billions of years. One of the most compelling pieces of evidence for these collisions comes from the presence of asteroid families. These are groups of asteroids that share similar orbits and compositions, suggesting they originated from a single parent body that was shattered in a massive collision. For example, the Flora family, one of the largest asteroid families in the main belt, is believed to have formed from the breakup of a single asteroid more than 100 kilometers in diameter. The fragments from this collision now orbit the Sun together, providing a snapshot of the destructive power of these impacts. But how do these collisions shape the asteroid belt? Over time, repeated impacts have ground down larger asteroids into smaller fragments, creating the diverse population of objects we see today. Some asteroids are now little more than loose collections of rubble held together by gravity. Others have been reshaped into bizarre forms, with elongated or irregular shapes that reflect their violent histories. These collisions also redistribute material across the asteroid belt, mixing different types of rock and metal and creating new opportunities for scientific discovery. The effects of collisions are not limited to the asteroid belt. Some asteroids knocked out of their original orbits by impacts have found their way to Earth as meteorites. These fragments provide direct evidence of the composition and history of their parent bodies, offering clues about the conditions in the early solar system. For example, the Allende meteorite, which fell in Mexico in 1969, contains tiny grains of material that predate the formation of the solar system itself, offering a glimpse into the cosmic environment that existed before the planets formed. Collisions also play a role in the ongoing evolution of asteroids. When two asteroids collide, the energy of the impact can melt or vaporize material, creating new minerals or altering the asteroid's surface. In some cases, the heat from a collision can even cause the asteroid to partially melt, leading to the formation of unusual features like metallic veins or glassy deposits. These processes not only change the asteroid's appearance but also its internal structure, making each collision a transformative event. As we study the evidence of past collisions, we gain a deeper understanding of the forces that have shaped the asteroid belt and the solar system as a whole. These impacts are not just destructive, they are also creative, driving the evolution of asteroids and contributing to the rich diversity of objects we observe today. With this in mind, we now turn to another fascinating aspect of asteroids, their unusual orbits and what they reveal about the history of our solar system. Now turning to the unusual orbits of asteroids, we find yet another layer of mystery in these celestial wanderers. While many asteroids follow predictable paths within the asteroid belt, some defy expectations with highly elliptical or inclined orbits that set them apart from the rest. These peculiar trajectories are not just random quirks, they hold vital clues about the origins and history of these space rocks. Asteroids with highly elliptical orbits, for instance, travel in elongated paths that bring them much closer to the Sun at certain points and much farther away at others. This extreme variation in distance can be a sign of past gravitational interactions with larger bodies, such as planets. For example, an asteroid might have been nudged into its current orbit after a close encounter with Jupiter, whose immense gravity can dramatically alter the paths of smaller objects. These interactions can even fling asteroids out of the asteroid belt entirely, sending them on new trajectories that cross the orbits of planets, including Earth. Inclined orbits, on the other hand, are those that are tilted relative to the plane of the solar system. Most objects in the solar system, including planets and many asteroids, orbit the Sun in a relatively flat disk. But some asteroids buck this trend, following paths that are steeply inclined. This can indicate that these asteroids originated from outside the main asteroid belt, perhaps from the outer reaches of the solar system. Some scientists believe that these inclined asteroids could be remnants of ancient collisions or even fragments of comets that have lost their icy tails over time. The study of these unusual orbits also sheds light on the dynamic history of the solar system. By analyzing the paths of these asteroids, scientists can piece together the gravitational forces that have shaped their journeys. For example, an asteroid with a highly elliptical orbit might have been influenced by the gravitational pull of a passing star or the early migration of giant planets. These clues help us reconstruct the chaotic environment of the early solar system, when collisions and gravitational interactions were far more frequent than they are today. Moreover, the orbits of these asteroids can reveal their potential future paths. Some asteroids with unusual orbits are classified as near-Earth objects, meaning they could one day come close to our planet. Understanding their trajectories is crucial for assessing the risk of potential impacts and developing strategies to mitigate such threats. By studying these orbits, scientists can predict where these asteroids are headed and how they might interact with Earth or other planets in the future. As we explore the unusual orbits of asteroids, we gain a deeper appreciation for the complexity and diversity of these celestial bodies. Their paths through space are not just random, they are a testament to the forces that have shaped the solar system over billions of years. With this in mind, we now turn to another intriguing aspect of asteroids, their surface composition and what it reveals about their formation and evolution. Now turning to the surface composition of asteroids, we uncover yet another layer of their fascinating diversity. Asteroids are far from uniform. Their surfaces can range from rocky and metallic to icy, each type offering unique insights into their origins and evolution. Understanding these compositions not only helps us classify asteroids, but also reveals the processes that shaped them over billions of years. Rocky asteroids, often referred to as stony or silicate-rich asteroids, are among the most common. These asteroids are composed primarily of silicate minerals, similar to the rocks found on Earth. Their surfaces are often covered in regolith, a layer of loose, fragmented material created by countless impacts over time. By studying these rocky surfaces, scientists can infer the conditions of the early solar system, as these asteroids are thought to be remnants of the building blocks that formed the inner planets. Metallic asteroids, on the other hand, are rich in metals like nickel and iron. These asteroids are believed to be the cause of ancient protoplanets that were shattered by massive collisions. The exposed metal surfaces of these asteroids provide a rare glimpse into the interiors of what might have been early planets. Some metallic asteroids even contain valuable resources, sparking interest in their potential for future space mining. The presence of these metals also tells us about the intense heat and pressure that once existed in the early solar system, which allowed dense metals to sink to the cores of these bodies. Icy asteroids, though less common, are equally intriguing. These asteroids are composed of water ice and other volatile compounds, often resembling comets more than traditional asteroids. Their icy surfaces suggest that they originated in the colder, outer regions of the solar system, where temperatures were low enough for water to freeze. The discovery of icy asteroids challenges the traditional view of asteroids as dry, rocky bodies and raises questions about the distribution of water in the solar system. Some scientists believe that icy asteroids could have played a role in delivering water to Earth, contributing to the formation of our oceans. Determining the composition of an asteroid's surface is no simple task. Scientists rely on a variety of methods, including spectroscopy, which analyzes the light reflected off an asteroid's surface to identify its minerals and compounds. Spacecraft missions such as Hayabusa and OSIRIS-REx have also provided direct samples and high-resolution images, offering unprecedented insights into asteroid surfaces. These missions have revealed that many asteroids are not uniform, but instead have patchy surfaces with varying compositions, hinting at complex histories of collisions and geological activity. The diverse surface compositions of asteroids are more than just curiosities. They are windows into the past. Each type of asteroid tells a different story about the formation and evolution of the solar system. Rocky asteroids remind us of the chaotic early days when planets were forming. Metallic asteroids reveal the violent collisions that shaped their cores, and icy asteroids hint at the distant, frozen regions where they originated. Together, these compositions paint a vivid picture of the dynamic and ever-changing nature of our solar system. With this understanding of asteroid surfaces, we now turn to another intriguing aspect: what lies beneath. The interiors of asteroids hold even more secrets, waiting to be uncovered as we continue our exploration of these enigmatic celestial bodies. Now turning to the interiors of asteroids, we delve into the hidden depths of these celestial bodies where even more mysteries await. While the surfaces of asteroids offer a wealth of information, their interiors hold the key to understanding their true nature and history. Scientists have pieced together clues about what lies beneath using a combination of observations, models, and data from spacecraft missions. One of the most surprising discoveries is that many asteroids are not solid rocks, but rather loosely bound collections of rubble. These rubble pile asteroids are held together by gravity, with their interiors consisting of fragmented material from past collisions. This structure explains why some asteroids have such low densities, as the gaps between the fragments create a porous interior. The Rubble Pile model also helps us understand how asteroids can survive high-speed impacts without completely shattering, as the loose material absorbs and redistributes the energy. Another fascinating aspect of asteroid interiors is the presence of voids or empty spaces. These voids can form when smaller fragments are ejected during collisions, leaving behind hollow regions. In some cases, these voids can even create caverns or tunnels within the asteroid. The existence of such features challenges the traditional view of asteroids as dense, solid bodies and highlights the complexity of their internal structures. Scientists have also used seismic data and impact experiments to infer the properties of asteroid interiors. For example, when a spacecraft deliberately collides with an asteroid, the resulting vibrations can reveal information about the asteroid's internal composition and density. These experiments have shown that some asteroids have layered interiors, with denser materials at the core and lighter materials near the surface. This layering suggests that these asteroids may have undergone differentiation, a process where heavier elements sink to the center while lighter materials rise to the top. The study of asteroid interiors has important implications for understanding their formation and evolution. For instance, the presence of rubble pile structures suggests that many asteroids are the remnants of larger bodies that were shattered by collisions. The voids and caverns within asteroids provide clues about their violent histories, while the layered interiors hint at processes like differentiation that were once thought to occur only in planets. Understanding the interiors of asteroids is not just an academic exercise, it has practical applications as well. For future missions aiming to land on or mine asteroids, knowing their internal structure is crucial for planning and safety. A rubble pile asteroid, for example, would require different landing strategies than a solid, dense one. Similarly, the presence of voids could pose challenges for mining operations, but also offer opportunities for creating habitats or storage spaces. As we continue to explore the interiors of asteroids, we uncover more about the dynamic processes that shaped these ancient bodies. From rubble piles to layered cores, each discovery adds a new piece to the puzzle of our solar system's history. With this deeper understanding, we are better equipped to unlock the secrets of these enigmatic objects and harness their potential for future exploration. Now turning to the remarkable achievements of asteroid missions, we explore how spacecraft like Hayabusa and OSIRIS-REx have revolutionized our understanding of these ancient celestial bodies. These missions have not only brought us closer to asteroids, but have also provided unprecedented insights into their composition, history, and potential for future exploration. The Hayabusa mission, launched by Japan's space agency, was a groundbreaking endeavor that successfully returned samples from the asteroid Itokawa. This marked the first time humanity had ever retrieved material directly from an asteroid and brought it back to Earth. The samples revealed that Itokawa is a rubble pile asteroid, confirming earlier theories about its loose, fragmented structure. The mission also provided valuable data on the asteroid's surface properties, helping scientists understand how such bodies evolve over time. Similarly, NASA OSIRIS-REx mission has been a game-changer in asteroid exploration. This spacecraft traveled to the near-Earth asteroid Bennu, where it collected samples from its surface. The mission revealed that Bennu is not only rich in carbon but also contains water-bearing minerals, suggesting that asteroids like Bennu may have played a role in delivering water and organic molecules to early Earth. The detailed images and data from OSIRIS-REx have also shown that Bennu's surface is surprisingly dynamic, with particles being ejected into space and boulders shifting over time. These findings challenge our assumptions about the stability of asteroid surfaces and highlight the need for further study. These missions have transformed our understanding of asteroids, showing us that they are far more complex and diverse than we once thought. They have also demonstrated the feasibility of sample return missions, paving the way for future endeavors to bring back even more material from these ancient bodies. The data collected by Hayabusa and OSIRIS-REx have provided critical insights into the formation and evolution of the solar system, as well as the potential resources that asteroids may hold. Looking ahead, asteroid missions hold immense promise for both scientific discovery and practical applications. Future missions aim to explore new types of asteroids, study their interiors, and even test technologies for asteroid mining. By continuing to push the boundaries of exploration, we are not only unlocking the secrets of our cosmic past, but also laying the groundwork for humanity's future in space. As we prepare for the next chapter in asteroid exploration, the discoveries made by missions like Hayabusa and OSIRIS-REx remind us of the endless possibilities that await us among the stars. Now turning to the potential dangers lurking in the cosmos, we delve into the topic of asteroid threats and the risks they pose to Earth. While asteroids have fascinated scientists for their scientific value, some of these celestial bodies also present a real and present danger. Asteroids large enough to cause significant damage upon impact are rare, but the consequences of such an event could be catastrophic. This has led scientists to focus on tracking near-Earth asteroids and developing strategies to mitigate the risks they pose. To monitor these potential threats, astronomers use a combination of ground-based telescopes and space observatories. Programs like NASA and Near-Earth Object Observations (NEO) track the orbits of asteroids, calculating their paths to determine if they pose any risk of collision with Earth. By cataloging these objects, scientists can predict potential impacts years or even decades in advance, giving humanity time to prepare or take action. One of the most well-known examples of a near-Earth asteroid is Apophis, which initially caused concern when calculations suggested a small chance of impact in the year 2029. Further observations ruled out this possibility, but Apophis remains a reminder of the importance of vigilance. Another example is the Chelyabinsk meteor, which exploded over Russia in 2013, releasing energy equivalent to around 30 times that of the Hiroshima atomic bomb. While it caused no direct fatalities, the event highlighted the need for better detection systems for smaller asteroids that could still cause significant damage. To address these threats, scientists and engineers are developing innovative strategies to deflect or destroy hazardous asteroids. One approach involves using kinetic impactors, spacecraft designed to collide with an asteroid to alter its trajectory. NASA's Double Asteroid Redirection Test (DART) mission successfully demonstrated this technique in 2022, impacting the asteroid Dimorphos to change its orbit. Another proposed method involves using gravity tractors, spacecraft that would fly alongside an asteroid, using their gravitational pull to gradually shift its path over time. In addition to these technological solutions, international collaboration is key to addressing the asteroid threat. Organizations like the United Nations Office for Outer Space Affairs, UNOOSA, work to coordinate global efforts in asteroid detection and mitigation. By sharing data and resources, countries can enhance their ability to respond to potential threats and protect our planet. As we continue to explore the mysteries of asteroids, the lessons learned from missions like Hayabusa and OSIRIS-REx not only deepen our understanding of these ancient bodies, but also equip us with the knowledge to safeguard Earth from potential impact. The ongoing efforts to track and mitigate asteroid threats remind us of the delicate balance between curiosity and caution in our journey through the cosmos. With each discovery, we move closer to ensuring that humanity remains prepared for whatever challenges the universe may bring. Now turning to the next frontier in space exploration, let's explore the fascinating concept of asteroid mining. Imagine a future where we no longer rely solely on Earth's dwindling resources, but instead harvest valuable materials from asteroids. These celestial bodies are treasure troves of precious metals, rare minerals, and even water, which could revolutionize industries both on Earth and in space. But how feasible is this idea, and what challenges stand in the way? Asteroids are rich in resources like platinum, gold, nickel, and iron, as well as rare earth elements essential for modern technology. Some asteroids are estimated to contain trillions of dollars worth of these materials. For example, a single asteroid like 16 Psyche, believed to be composed largely of metal, could hold enough iron and nickel to meet global demand for millions of years. Beyond metals, water ice found on certain asteroids could be broken down into hydrogen and oxygen, providing fuel for spacecraft and supporting long-term missions to the Moon, Mars, and beyond. However, mining asteroids is no simple task. The technological challenges are immense. First, there's the issue of reaching these distant objects. Asteroids are often millions of miles away, requiring advanced propulsion systems and spacecraft capable of enduring the harsh conditions of deep space. Once there, extracting resources in microgravity environments poses another hurdle. Traditional mining techniques used on Earth won't work in space, so engineers are developing innovative methods such as robotic drills, 3D printing, and even using solar energy to vaporize and collect materials. Another major challenge is the cost. Developing the technology and infrastructure for asteroid mining requires significant investment, and the economic viability of such missions is still uncertain. Companies like Planetary Resources and Deep Space Industries have explored the concept, but the high upfront costs and risks have slowed progress. Governments and private companies will need to collaborate to make asteroid mining a reality. Despite these challenges, the potential benefits are enormous. Asteroid mining could reduce the environmental impact of mining on Earth, which often involves deforestation, pollution, and habitat destruction. In space, harvested resources could support the construction of habitats, fuel depots, and even spacecraft, enabling deeper exploration of the solar system. Water from asteroids could sustain life and provide fuel for missions, making it a key resource for establishing a sustainable presence beyond Earth. As we look to the future, asteroid mining represents a bold step toward a new era of space exploration and industry. While the road ahead is filled with obstacles, the rewards could be transformative, unlocking resources that fuel humanity's expansion into the cosmos. With continued innovation and collaboration, the dream of mining asteroids may one day become a reality, reshaping our relationship with the universe and securing a prosperous future for generations to come. Now turning to the future of asteroid exploration, let's dive into the exciting missions that are set to expand our understanding of these mysterious space rocks. Scientists and space agencies around the world are gearing up for a new wave of missions that promise to unlock even more secrets hidden within asteroids. These missions aren't just about studying these celestial bodies, they're about bringing pieces of them back to Earth and exploring new types of asteroids that could reshape our understanding of the solar system. One of the most anticipated missions is NASA OSIRIS-REx, which successfully collected samples from the asteroid Bennu and is now on its way back to Earth. These samples are expected to arrive in 2023, offering scientists a treasure trove of material to analyze. By studying these samples, researchers hope to learn more about the early solar system, the origins of organic molecules, and even the potential for asteroid resources to support future space exploration. Meanwhile, Japan's Hayabusa 2 mission has already returned samples from the asteroid Ryugu, revealing surprising details about its composition and history. These findings have sparked new questions about how asteroids form and evolve, and they've set the stage for even more ambitious missions in the coming years. For example, the European Space Agency's Hera mission is set to explore the Didymos binary asteroid system, focusing on the aftermath of NASA's DART mission, which intentionally crashed into one of the asteroids to test planetary defense techniques. Hera will study the impact crater and gather data to help scientists better understand how to deflect potentially hazardous asteroids in the future. looking further ahead, NASA Lucy mission is on a groundbreaking journey to explore the Trojan asteroids which orbit the Sun alongside Jupiter. These asteroids are believed to be remnants of the early solar system, and studying them could provide clues about how planets formed and migrated over billions of years. Similarly, the Psyche mission is set to visit the metal-rich asteroid 16 Psyche, which could offer insights into the cores of rocky planets like Earth. The scientific goals of these missions are vast. By studying asteroids, scientists hope to uncover the building blocks of the solar system, understand the role of asteroids in delivering water and organic molecules to Earth, and assess the potential for mining these space rocks for valuable resources. Each mission brings us closer to answering fundamental questions about our place in the universe and the processes that shaped our cosmic neighborhood. As we look to the future, the possibilities for asteroid exploration are endless. From sample return missions to the study of exotic asteroid types, these endeavors promise to revolutionize our understanding of space and pave the way for humanity's next great leap into the cosmos. With each mission, we're not just exploring asteroids, we're uncovering the story of our solar system and preparing for a future where the resources of space could fuel our journey to the stars. Now turning to the conclusion of our journey through the bizarre and fascinating world of asteroids, let's take a moment to reflect on the incredible discoveries we've explored. From metallic spheres and organic molecules to water ice and strange magnetic fields, asteroids have proven to be far more complex and diverse than we ever imagined. These celestial bodies are not just lifeless rocks drifting through space, they are time capsules that hold clues to the origins of our solar system and the building blocks of life itself. Each discovery has expanded our understanding of the cosmos in profound ways. We've learned that asteroids can harbor water ice, challenging our assumptions about the dryness of space and opening up possibilities for future exploration. We've uncovered evidence of ancient volcanic activity and rubble pile structures, reshaping our ideas about how these objects form and evolve. And we've even found asteroids with moons, rings, and thin atmospheres, revealing a level of complexity that rivals that of planets. These findings have not only deepened our knowledge of the solar system, but also sparked new questions and possibilities. Could asteroids have delivered the water and organic molecules that made life on Earth possible? Could they hold the key to unlocking resources for future space missions? The answers to these questions are still unfolding, and each new mission brings us closer to uncovering the secrets of these enigmatic objects. As we look to the future, the potential for asteroid exploration is limitless. With missions like OSIRIS-REx, Hayabusa 2, and Psyche, we are on the brink of discoveries that could revolutionize our understanding of space and our place within it. These missions remind us that the universe is full of surprises, and there is still so much to learn. So, as we wrap up this exploration of 30 bizarre things scientists have found on asteroids, I encourage you to stay curious. Follow the latest developments in space exploration and keep an eye on the incredible missions that are pushing the boundaries of what we know. The story of asteroids is far from over, and who knows what strange and wondrous discoveries await us in the years to come. If you enjoyed this journey through the mysteries of space, don't forget to like, subscribe, and hit the notification bell so you never miss an update. Until next time, keep looking up, the cosmos is waiting.